Right now, at this very moment, there is a planet drifting through the darkness between stars with no sun to orbit, no source of light or heat, and no gravitational anchor tying it to anything. It is roughly the size of Earth, possibly larger. It has been traveling alone through interstellar space for what might be hundreds of millions of years. And NASA just found it using a detection method that was not supposed to work on objects like this. This is not science fiction. This is observation. The planet was detected in December 2025 during a microlensing survey conducted by the Nancy Grace Roman Space Telescope. Its designation is OGLE 2025 BLG 13449LB, and it represents one of the strangest categories of objects in the galaxy. A rogue planet, a world with no star, no orbit, no home system. Just endless motion through the void, traveling at speeds we can barely measure toward a destination it will never reach. What makes this discovery significant is not just that we found another rogue planet. We have suspected they exist for years. What makes this significant is how common the data suggests these objects actually are. If the analysis holds up, rogue planets might outnumber stars in the Milky Way by a factor of 10 or more. That would mean there are hundreds of billions of these dark, wandering worlds drifting unseen through our galaxy. And until now, we had no reliable way to detect them. If you want space science that explains discoveries without turning them into clickbait, subscribe to Space Horizon, because we are going to break down exactly how this planet was found, why it exists, and what it tells us about the violence of planetary system formation across the galaxy. Let us begin. To understand how NASA found a planet with no star, you need to understand gravitational microlensing. It is one of the stranger techniques astronomers use, and it only works under very specific conditions. The method relies on a prediction from Einstein's general theory of relativity. Mass bends space. When light from a distant star passes near a massive object, the path of that light curves. If the alignment is just right, the massive object acts like a lens, magnifying and brightening the light from the background star. This effect was first observed during a solar eclipse in 1919, when astronomers measured how light from stars near the sun's edge bent as it passed through the sun's gravitational field. That observation confirmed general relativity. A century later, astronomers are using the same physics to find planets. Here's how it works. Imagine a distant star thousands of light years away. Now imagine a planet much closer to us passing directly between us and that star. As the planet moves across our line of sight, its gravity bends the light from the background star. For a brief period, usually hours to days, the background star appears brighter. The amount of brightening and the exact shape of the brightness curve depend on the mass of the lensing object and how closely it passes in front of the star. If the lensing object is a star with a planet orbiting it, the light curve shows a characteristic double peak. One peak from the star, a smaller secondary peak from the planet. If the lensing object is a planet with no star, the light curve shows a single symmetric peak. That single peak is the signature. It tells you the lensing object has planetary mass, and it is alone. The challenge is that these events are rare and they never repeat. The alignment has to be nearly perfect. The planet has to pass almost exactly between us and a background star, and space is so vast that any given alignment happens only once. You cannot go back and observe it again. You get one chance, miss it, and the opportunity is gone forever. That is why detection requires constant monitoring of millions of stars, simultaneously waiting for one of them to suddenly brighten in just the right way. The Nancy Grace Roman Space Telescope, launched in March 2025, was designed specifically for this kind of work. Its wide-field camera can observe hundreds of thousands of stars at once, tracking their brightness with high precision, looking for the telltale signature of a microlensing event. On December 8, 2025, Roman detected a brightening event in a star located roughly 24,000 light-years away in the direction of the galactic bulge, the dense central region of the Milky Way. The star brightened by approximately 30% over a period of 6 hours, then faded back to its original brightness over the following 8 hours. The light curve was smooth, symmetric, single-peaked. Exactly what you would expect from a lone planetary mass object passing in front of a distant star. The team analyzing the data, led by Dr. Yuki Fujimoto at Osaka University, ran the numbers. The mass of the lensing object, based on the duration and amplitude of the event, came out to roughly 1.2 Earth masses. That puts it firmly in the terrestrial planet category. Not a gas giant, not a brown dwarf. A rocky world similar in size to Earth. But there was no star, no secondary light curve feature indicating a host star nearby, no infrared emission from a faint companion. The planet was alone. This is not the first rogue planet ever detected, but it is one of the smallest. Previous microlensing surveys have found larger rogue worlds with masses between 3 and 10 times Earth. Ogle 2025 BLG 1349LB is different because it is Earth-sized, and that raises uncomfortable questions about how it got there. Planets do not form in isolation. They form in protoplanetary disks, clouds of gas and dust surrounding young stars. Gravity pulls that material together. Dust grains stick, clumps grow. Eventually you get planetesimals, then planets. The entire process requires a star at the center, providing gravity to hold the disk together. Without a star, there is no disk. Without a disk, there is no planet. So if planets cannot form alone, how does a rogue planet exist? The answer is violence. Rogue planets are not born wandering. They are born in planetary systems and then ejected. Something gravitationally kicks them out of their home system with enough velocity to escape the star's gravity entirely. Once free, they drift through interstellar space indefinitely. There are a few ways this can happen. The first is planet-planet scattering. In a young planetary system, multiple planets form in orbits that are not perfectly stable. Over time, gravitational interactions between the planets can shift those orbits. If two planets come too close, one can gain energy and move to a more distant orbit, while the other loses energy, and either falls into the star or gets flung outward. If the ejection velocity is high enough, the planet escapes the system entirely. This process is not rare. Simulations of planetary system formation show that scattering happens frequently, especially in systems with multiple giant planets. Jupiter-sized worlds interact strongly. Their gravity is powerful enough to alter each other's orbits dramatically. Smaller planets like Earth-sized worlds get caught in the chaos. Some survive, some do not. Some get thrown out. The second mechanism is stellar encounters. Stars are born in clusters. In the dense environments of star-forming regions, young stars pass close to each other frequently. If a star with a planetary system has a close encounter with another star, the gravitational influence of the intruder can destabilize the planetary orbits. Planets in the outer part of the system are particularly vulnerable. A close pass can strip them away entirely, sending them into interstellar space. The third and most violent mechanism is supernova ejection. When a massive star explodes as a supernova, the blast can be asymmetric. If the explosion imparts a kick to the stellar remnant, it also disrupts any planets that were orbiting the star. Planets close to the star are vaporized. Planets farther out can be ejected at high velocities. Some of those ejected planets end up as rogue worlds. Any of these processes could have produced Ogle 2025 BLG 1349LB. We do not know which. We have no way of tracing the planet back to its origin. It has been traveling for millions, possibly hundreds of millions of years. Whatever system it came from is now far behind it, lost in the crowded star fields of the galaxy. What we can say is that the planet is cold. With no star to warm it, surface temperatures are determined entirely by internal heat left over from formation and radioactive decay in the core. For an Earth-mass planet, that internal heat is minimal. Surface temperatures are likely below minus 200 degrees Celsius. Any atmosphere it once had is probably frozen and precipitated onto the surface as ice. If there was ever water, it is now solid. Frozen oceans, frozen lakes, a world locked in permanent ice. But here is where it gets interesting. Some theoretical models suggest that beneath that frozen surface, conditions might be different. Radioactive decay in the planet's core generates heat. That heat has nowhere to go quickly. It accumulates. Over billions of years, it can create a temperature gradient, a frozen surface, a warm interior, and in between a layer where liquid water might exist. If that sounds far-fetched, consider Europa, one of Jupiter's moons. Europa has a surface covered in ice, but beneath that ice is a liquid ocean kept warm by tidal heating generated by Jupiter's gravity. Europa has no internal heat source other than the flexing caused by its orbit. A rogue planet has no tidal heating, but it does have radioactive decay. And some models suggest that for Earth-sized rogue planets, that decay might be enough to maintain subsurface liquid water for billions of years. If true, that raises the possibility, however remote, that rogue planets could harbor life. Not on the surface. Nothing survives in the cold and radiation of interstellar space, but deep underground in geothermally heated water protected from radiation by kilometers of rock and ice, simple microbial life might persist. It is speculative. It is unproven. But it is not physically impossible. The more immediate question is, how many of these objects exist? The fact that Roman found one Earth-mass rogue planet in just 9 months of operation suggests they are not rare. Microlensing surveys are not efficient. They only detect objects that happen to pass directly in front of a background star along our line of sight. The probability of any given rogue planet doing that is extraordinarily small. The fact that we detected one anyway means the total population must be huge. Dr. Fujimoto's team ran statistical models based on the detection rate. Their preliminary estimate published in February 2026 suggests there could be as many as 2 billion Earth-mass rogue planets in the Milky Way. That is a staggering number. For comparison, there are roughly 200 to 400 billion stars in our galaxy. If the estimate is correct, rogue planets are nearly as common as stars. And that is just Earth-mass rogues. Larger planets are easier to detect via microlensing because their stronger gravity creates brighter, longer-lasting events. Previous surveys have found rogue planets with masses up to 10 times Earth. If you include those, the total population could be even higher. Some estimates suggest the Milky Way contains more rogue planets than stars by a significant margin. Why does that matter? Because it tells us something fundamental about planetary system formation. If rogue planets are this common ejection, it must be a normal part of how planetary systems evolve. It is not a rare, catastrophic event. It is standard. Most planetary systems probably lose at least one planet during their formation. Some lose more. That has implications for our own solar system. Did the early solar system have more planets than it does now? Simulations suggest it might have. The current arrangement of planets is stable, but it did not start that way. In the first few hundred million years after formation, the giant planets likely migrated. Jupiter moved inward, then outward. Saturn, Uranus, and Neptune shifted positions. In the chaos, smaller planets could have been lost. There is some indirect evidence for this. The asteroid belt between Mars and Jupiter is a region that never formed a planet. One explanation is that a planet did form there but was later ejected or destroyed. The NICE model, a widely accepted theory of solar system evolution, suggests that a fifth giant planet may have existed in the early solar system and was later ejected during a period of orbital instability. If that happened, the ejected planet is now a rogue somewhere in the galaxy, indistinguishable from the billions of others. We would have no way of knowing it was once part of our system. Detecting more rogue planets will require continued monitoring. The Roman Space Telescope is conducting ongoing microlensing surveys targeting the galactic bulge, where background stars are densest and detection probabilities are highest. Each new detection refines the population estimates and helps constrain models of planetary system dynamics. There is also a longer-term possibility. If rogue planets are as common as the data suggests, some of them are much closer to us than Ogle 2025 BLG 1349LB. There could be rogue planets passing through the outer solar system right now. They would be dark, cold, nearly impossible to detect with current technology. But future infrared surveys, particularly those conducted by next-generation space telescopes, might be able to find them. If we could identify a nearby rogue planet, it would become an obvious target for a robotic mission. A spacecraft could be sent to study it up close, image the surface, measure the composition, search for subsurface water. It would be one of the strangest missions ever attempted. A journey to a world with no sun, no day, no night, just eternal darkness. The discovery of Ogle 2025 BLG 1349LB is a reminder that planets are not always where we expect them to be. We think of planets as objects that orbit stars, but the galaxy is full of exceptions. Worlds that broke free, worlds that drift alone, worlds that have seen things we can barely imagine. The violence of their ejection, the silence of their journey, the cold of interstellar space. These planets are not dead. They are not gone. They are out there, billions of them, wandering through the darkness between stars, carrying whatever history they accumulated before they were cast out. And now for the first time, we have the tools to find them. If you want to follow this story as more rogue planets are discovered, subscribe to Space Horizon. We will be tracking the Roman mission's microlensing results and breaking down each new detection. Turn on notifications so you do not miss it. Leave a comment and tell me what you think happens to a planet after it gets ejected. Does its atmosphere freeze immediately? Could liquid water survive underground? Could life persist in the deep subsurface warmed by radioactive decay? These are open questions, and I want to know what you think. Share this video with someone who still thinks planets need stars because the galaxy just proved otherwise. Ogle 2025 BLG 1349LB is out there right now, drifting through interstellar space. Alone, dark, and impossibly far from anything we would recognize as home. Thanks for watching Space Horizon. We will see you in the next one.